Hello guys, welcome to another video. Today we're going to work in topic 4 in a couple of multiple choice questions. So let's jump straight into it and see the solutions of the problem. So here we have the problem number one. It says a particle performs simple harmonic motion. What is the phase difference between the displacement and the acceleration of the particle? So here you know in the simple harmonic motion that acceleration is directly proportional with the displacement but in the opposite direction. So that means whenever this is maximum as well, but they have opposite directions. So of course, this gives you a phase difference of p radians. Number 2, which graph shows the variation with time of the kinetic energy of an object undergoing simple harmonic motion of period t? So let's see what we have here. Let's say that we have a spring, and this is isolating between the two extreme positions, here and here. So now you see that this is the equilibrium position. So you see that a whole period, it's gonna be from the object to move from this position A all the way to this position B and back as well. So that gives you that you pass through the equilibrium position 2 times. So you have 2 times maximum velocity. So with maximum velocity, you have also kinetic energy. So you need to have 2 times maximum kinetic energy in one period. So it cannot be B, it cannot be C. Now what is happening between the A choice and the B choice? You see that in the A choice you have negative energy. But you know that kinetic energy is proportional with a velocity square. So that means that you will never have negative kinetic energy. It doesn't matter of the direction of velocity if you go to the right or to the left. So of course the correct choice here is D. So number 8, we have the graph show the variation of the displacement y of a medium with distance x and with time t for a traveling wave. What is the speed of the wave? So here, when we have the displacement against distance, what we can do is y against x, we can find the wavelength. So the wavelength here, you can see that it is 8 meters. And when we have displacement against time, you can find the period. And the period you can see it's 10 milliseconds. So we can use this very famous equation in order to calculate the speed of the wave. Of course, we're going to take the frequency as 1 over t, and here we're going to replace the numbers. 8 meters divided by 10 times 10 to the power of negative 3 seconds, and if you do the math here, you can find that is 800 meters per second. So correct answer is D. The next one, it says that L is a point source of light. The intensity of the light at a distance 2x from L is I. What is the intensity at a distance 3x from L? So what we have here, we know that the intensity is inversely proportional with a distance squared. The intensity I that we have for the 2x distance, it's going to be 1 over 2x squared. So this is going to be 1 over 4x squared. The new intensity that we are looking for, let's call it I prime, it's at distance 3x away from the source. So this is going to be 1 over 9x squared. And now somehow I need to create this relationship here in order to find the relationship between I prime and I. So the easiest way to do is to multiply both numerator and denominator with 4. So having this, you see that you can have 4i. So this is I. So the correct answer here is A. The next one, this is on 4.3. It asks which of these waves cannot be polarized. And of course, this is something very simple to answer. We know that the sound waves, they're longitudinal waves, so they cannot be polarized. So the answer, of course, is number B. Number 2, it says that unpolarized light is incident on 2 polarizers. The axes of polarization of both polarizers are initially parallel. The second polarizer is then rotated through 360 degrees as shown. Which graph shows the variation of intensity with angle theta for the light leaving the second polarizer? So what do we see here? First, unpolarized light will enter the first polarizer and it's gonna be polarized in this direction. In the second polarizer, it's gonna start to rotate for a full circle. So what's gonna happen? At 90 degrees, if this is the direction of polarization initially, when it enters, it will enter with maximum intensity. At 90 degrees, you will have zero intensity. At 180 degrees, you are going to have maximum intensity again. At 270 degrees, you are going to have zero intensity. At 360 degrees, you are going to have maximum intensity again. And of course, when it enters, it's going to be maximum as well. So this is what we're looking for. We're looking for three different maximas during the rotation. And of course, the answer here, it can be only B. As you can see, maximum at 180, maximum at 360, maximum at 0. And of course, 0 at 90 and 270. Number 3, it says two wave pulses, each of amplitude A, approach each other. They then superpose before continuing in their original directions. What is the total amplitude during superposition and the amplitudes of the individual pulses after superposition? So let's see the individual ones. After, of course, it's gonna be the same. You cannot have less than this, you don't lose any energy. And for the total amplitude during superposition, you see that they're going to add up together and it's gonna give you 2A. So the correct answer here is D. Now a similar one, number 4, it says two pulses are traveling towards each other. What is a possible pulse shape when the pulses overlap? So you see that they have this specific shape and they move towards each other. So of course, when they add up, they're gonna have the exact same shape, but with higher amplitude. So of course, answer here is A. Cannot be any of the other ones. Number 5. It says unpolarized light of intensity I0 is incident on the first of two polarizing sheets. Initially, the planes of polarization of the sheets are perpendicular. Which sheet must be rotating and by what angle so that light of intensity I0 over 4 can emerge from the second sheet? So let's see what we have. We have unpolarized light, first of all, of intensity I0. It will enter two polarizers with this plane of polarization. So from after the first one, polarized light, it's gonna emerge with intensity I0 over 2, the half of it. And then we need to rotate this one in order to have incident emerged light of intensity I0 over 4. I0 over 4. Now, which of those we need to rotate, it doesn't matter. We can rotate either the first one, either the second one. It doesn't really matter for us. The angle will be the same. It doesn't matter if you enter with a specific perpendicular plane or with another specific plane with an angle. Okay, so it can be either C, either D. Now, for the emerged light intensity, what we have to do is to use Malus law. So what you want to have here, you want to have I0 over 4 emerged light. And before you enter with I0 over 2 cos square theta. So now we need to resolve this relationship for theta. So from here I have cos square theta, it's 1 over 2. I'm taking the square root of this, it's 1 over the square root of 2. So from here, I'm going to solve for the angle theta, that it's cosine minus 1, 1 over square root of 2. And now you will tell me, but there is no option like this. Well, there isn't, but the 1 over square root of 2, what you can do is to multiply both with the square root of 2, up and down, and it's going to give you square root of 2 over 2. So it's the same thing if you have the cosine to the power of negative 1 of square root of 2 over 2. So this is your answer. And of course, these are your options. So it's number C. Number 6. Properties of waves are polarization, diffraction, and refraction. Which of these properties apply to sound wave? So sound waves, it's, as I said before, longitudinal waves, so polarization, it doesn't apply. So the correct answer here, of course, is C, only diffraction and refraction. 7. A point source emits sound waves of amplitude A. The sound intensity at a distance d from the source is I. What is the sound intensity at a distance 0.5 d, so half the distance from the source, when the source emits waves of amplitude 2I? So what do we have here? We have two relationships between intensity and amplitude, and between intensity and the distance between the source and wherever you try to see it. And you know that the intensity I, it comes from an amplitude A square, and also the intensity I, it comes from a distance d square. And what you will have to do here is to use intensity of amplitude 2A square and intensity of distance 0.5 d. So your new intensity is going to be 2A, all of it square, so it's going to be 4A square. So it's going to be 4 times I, the intensity before. Also your new intensity, it's going to be 1 over 0.5 d square. And it's going to give you 1 over 0.25 d square. So this is 1 over 0.25, it's 4I, 1 over d square, as it was before. So if you combine both of those, you will have 16I intensity. So the correct answer here is A. Now the next ones are from the 4.4. It says that monochromatic light is used to produce double-slit interference fringes on a screen. The fringe separation on the screen is Y. The distance from the slits to the screen and the separation of the slits are both doubled, and the light source is unchanged. What is the new fringe separation on the screen? So from here, we know that we have the fringe separation on the screen to be Y initially, when you have the specific distance d, capital, and small d, the distance between the slits, and the screen. Now the wavelength is unchanged because the light source is unchanged. Now your new separation, it's gonna be the double distance from the screen and also the double distance between the slits. So from here, you're going to have the same relationship as before. So it's going to be just Y as well. So here the answer B. Now number 2, monochromatic light is traveling upwards in glass and is incident on a boundary with air. The path of the refracted light is shown here. So here we see that we enter with a critical angle theta. A layer of liquid is then placed on the glass without changing the angle of incidence on the glass. The refractive index of the glass is greater than the refractive index of the liquid, and the refractive index of the liquid is greater than of the air. What is the path of the refracted light when the liquid is placed on the glass? So since we don't change the angle of incidence, again, you enter with critical angle. Now it doesn't matter what you place in between a liquid, for example here, as long as the refractive index is in between of the other refractive indexes of glass and air, it's going to give you the exact same path of the refracted light. So answer here is D. Now the 11, it says that X and Y are two coherent sources of waves. The phase difference between X and Y is 0. The intensity at P due to X and Y separately is I. The wavelength of each waves is 0.20 meters. What is the resultant intensity at P? So we're looking at the intensity here at P. So first we need to see if we have constructive or destructive interference in this case. Now from here, we need to check the path difference between these two different lights. And the path difference it's shown to be 0.4, the subtraction between these two lines. The wavelength is 0.2 meters. So that means that the path difference, it is 2 times lambda. So that shows constructive interference. So that means that the intensity of each one of amplitude A, it's gonna be added together, so you will have an amplitude of 2A squared. So the intensity here it will be 4A squared, so it's gonna be 4 times the initial intensity I. So here the correct answer is D. 12. Light is incident at the boundary between air and diamond. The speed of light in diamond is less than the speed of light in air. The angle of incidence I of the light is greater than the critical angle. Which diagram is correct for this situation? So here we know that the incident angle is greater than the critical angle. So that means total internal refraction. So from here, it cannot be D, it cannot be B. Now between A and C, when you have total internal refraction, the other boundary that you have to have is that the light, it passes from the denser medium to the lighter one, to the less dense. So of course here it's the choice A, cannot be choice C, because it comes from air to diamond. We want the opposite, denser to less dense. Now the next one comes from the topic 4.5, standing waves, and we have for the first one, a student blows across the top of a cylinder that contains water. A first harmonic standing sound wave is produced in the air of the cylinder. More water then is added to the cylinder. The student blows so that a first harmonic standing wave is produced with a different frequency. What is the nature of the displacement in the air at the water surface and the change in frequency when the water is added? So here what we have first of all the first harmonics in both situations. So first harmonic in a pipe with one closed end and one open end, and they create it like this. So from here, of course, the nature of displacement for the air at the water surface, of course, it will be a node. It cannot be an antinode. The change in frequency now. We see for the first one, if this is distance L, we have that the distance L is lambda over 4. And now for the second one, if this distance is L prime, we know that the L prime is lambda prime over 4. And now from here you see that the L is bigger than the L prime. So that means that the lambda will be bigger than lambda prime as well. And from the equation, V is lambda times F, when the speed is constant, because it moves through the same medium. So from here you can see that the bigger wavelength, it's gonna give you smaller frequency. So the frequency here is increasing. So these are your choices, of course, number D. Number 2, it says that in an experiment to determine the speed of sound in air, a tube that is open at the top is filled with water and a vibrating tuning fork is held over the tube as the water is released through a valve. An increase in intensity in the sound is heard for the first time when the air column length is X. The next increase is heard when the air column length is Y. So we have the first and we have the second harmonic as well. Which expressions are approximately correct for the wavelength of the sound? So what we need to do here is to check our wavelength for the distance X when the water is filled up until that point, X. So here you see, of course, the first harmonic, and this distance X is equal with lambda over 4. So one expression for lambda is 4 times X. So 1 is correct. And then if I do the same for the distance Y, that is somewhere here, this distance Y, here I see the next harmonic. The next harmonic it is like so. So this distance y, it's 3 lambda over 4. So the expression for lambda is going to be 4y over 3. So also the third one is one of your choices. So here, of course, correct answer is B, 1 and 3. And now the last one, it says that a third harmonic static wave of wavelength 0.8 meters is set up on a string fixed at both ends. 2 points on the wave are separated by a distance of 0.6 meters. What is possible phase difference between the 2 points on the wave? So here, first of all, what we have to do is to find the length of this string. Now we have a third harmonic on a string fixed at both ends. So this length is gonna be given by the expression of 3 times lambda over 2. And if you do the math here, 3 times 0.8 divided by 2, it's gonna be 1.2 meters. So let's try to draw the situation here. Here your string, the 2 fixed ends. We have the length to be 1.2 meters from the 2 different ends. And also, we have the third harmonic, so we're going to have 3 loops. So this is the shape that I get in a string with a fixed end, with both ends fixed and the third harmonic. So each loop, it has to have 0.4 meters distance between the nodes from the other one. And now we need to check 2 different points that are separated by a distance of 0.6. So what we can do here, we can take different situation. Let's say that we take the first one, let's say at 0.3 here. So this is your first. And then the next point, it needs to be separated by 0.6 meters. So you have to go all the way to see where it's the next one. And it's gonna be at 0.9. So somewhere here, 0.9. Now this difference between these 2 different points, it's 0 radians. Okay, because they are in the same loop or in every other loop, they have 0 phase difference. But you don't have any of these options here. So let's try to find maybe another point. So let's take the point of 0.1 and the point of 0.7 that will be somewhere here, 0.7. So these ones, they're adjacent loops. The adjacent loops, they have a phase difference of pi rads. So of course your answer here is C. So that's it for today, guys. You need to study hard and I wish you good luck.